Hello, and transcription also started, so apparently you can hear me, or you will be able to hear me well. Today we are going to do the practical, which is a little perhaps deviating from the from our normal route along the assignments essentially. But the point here is that we have covered all necessary bits and pieces for the assignment to be complete, and you have all the information essentially to do the assignment, so you don't need to get anything else. And today is a further extension of our modeling exercises. We will look at how to perform a little bit more complicated data analysis, and also we will look at how to do cross-validation in R. There are quite obviously, there are straightforward means, libraries and functions to use to perform cross-validation of the model. Of course, we have already done the linear modeling, and GLM and GAM as well, and we have done that, and we compared the quality of the models using AIC. But here we look at the other type of model verification and checking the model performance and choosing the model as well. So, oh, right, Parminder has come, but okay, so anyway, I'm just doing the recording. You are alone in this room, so yeah. So this is what our practical today will be about. First of all, we will look at how to make a bit more complicated models, and how to also think in the sense of interaction terms or crosstalk between different features. And also then we will see how to do the cross-validation and how to check the model when we are cross-validating it. In any case, this is what you in principle don't need to do in the assignment unless you really want to. So there is literally no task to cross-validate the generated models, because in principle you can do it, but there is literally there is no need. So we use all the data, and we are fine about that. Yeah. So let's just to remind you, there is the due date for the assignment, right? And this due date is this Friday. Today I think I have released the marks for the quiz, so you can go and check yourselves. And this is the last practical with the with like new material. The next one will be also interesting, so maybe you want to come and see that as well. But anyway, so let's start with the practical. As we have identified here, our learning goal is to use the nested data frames, or to learn how to use the nested data frames, and how to use the R sample to perform cross-validation. Okay, so let's start and go through the practical again. We are going to use the data set which is called Gapminder. Now, this data set is very interesting because it has different countries, different continents. Then it has the information for the life expectancy, population, and GDP per capita for all those different countries on different continents. And also there is the year variable when that data was measured, right? So it's quite an interesting data set, and I do recommend you go and check how it looks like and what else you can do. with it. But anyway, let's start first with doing the linear model, right? And we pick Australia as a country, so we run it. And what we do is we take the data set Gapminder, we filter by the country, which is Australia, and then we create Australia model, which is the linear model where we look at the dependency between, or well, at the correlation between the population and the year, right? So we do expect the population to grow, and again, we take the data set aus, which we have created here, right? So we can run it, and it will create the model, the linear model in this case. What we do next is, well, probably a little bit different from what you have seen before. We use the library Mosaic, which has a function which is called plot model. And if we run it, it will plot the population versus year, but it will plot the data in the form of those points, right? And it will plot the regression line, which is just the horizontal, sorry, not the horizontal, but this diagonal black line. This is the regression line. So you can see again how those models are constructed. They sort of nicely fit all the points. So the straight line is located somewhere in like in between of those points and nicely crossing the cloud of points in the middle. So you can see that the model is quite good, and indeed, the population is dependent on the year for Australia, and it grows linearly, at least in the range between like 1950 and 2010. Okay, we can also do multiple or multidimensional linear regression. To do that, now we specifically make here an example which is more complicated than just straight line. You will see it in a second, right? So first of all, we filter out by year, right? So we will have all the countries in there and all the continents, but we'll have also the life expectancy, GDP, and so on. And we will be able to link those variables and see if there is an interesting dependence. And indeed there is, because if we plot a simple linear model, we will see this. So again, we took our newly created life expectancy 2007 dataset, and then we tried to correlate life expectancy and GDP per capita, right? And then we plotted the model, again, using the same function from the above, from Mosaic library. So what we see is a little bit, well, not a little bit, but definitely different from the previous case where we had a nice straight line. Here we don't have a straight line anymore. Here we have some sort of a hook-like structure. But again, we need to remember that this data contains all countries, all continents, everything for that particular year, right? So we can see that the fit is not good here, definitely. So the fit is quite poor, and the data, if we plot it this way, clearly exhibits nonlinear dependency, which we are trying to approximate with a straight line. So it doesn't really work well. What we want to do in this case is probably advance the model, right? So we want to add a new variable into the model, which is continent, right? And we create life expectancy model number 2, where we update the model 1 with a new variable continent. So you can see how we updated the model without recreating the previous one. And in this case, when the data set is small, it probably doesn't matter because it will run in the blink of your eye, and that's essentially it. But if there are bigger models, it may make a difference. And again, this sort of a way of defining the model is quite nice, right? So you can add and remove the variables from the model. Okay, so let's run it. And now we have something different. So first of all, since we added here the continent variable, and continent variable, of course, is not a metric variable, right? This is a variable which is categorical and nominal because sorting doesn't make sense. We have literally created like five linear models, right? Each of the linear models corresponds to a separate straight line in this case. Okay. Now we can see that it is already better in principle, right? So there is this red line for Africa. There is the green line, which is sort of fitting it, and so on. The only problem is when we describe it this way, we automatically create the requirement of the same slope for all those separate models or submodels, if you want, for different continents. Okay, so what we think is that, okay, there is the dependency between the continent and the linear term, right, in the model. So what we want to tell the model is that we need a different slope for each of the continents. And to declare this possibility, we need to use the interaction term. And here we include this interaction term. So we take the previous model, which is life mod 2, right? Which includes the both the continent and the GDP, right, per capita, and we add the interaction term. Okay, then when we plot it, we immediately see the difference, right? So all those models now, or submodels, have different slopes, and all those models now can work sort of independently. Nevertheless, all of them are collated in one single model. So one single model in this case can be used, to make predictions and to do other things, whatever you want to do with the model. Yeah. Okay. So now you can, in principle, you can see that that all those have have different slopes, and if you compare here with the previous example, you will see that that it's the African continent which has the most different slope here. Okay, right. Right. So that was about how the interaction terms work and how we can also, so I mean, being able to plot the model with this thing is also quite a nice tool. The only problem is this plot model, as far as I know, maybe they have already changed it, but as far as I know, it works only with linear models and GLMs. So it doesn't work with GAMs. Okay? Yeah. Okay, so, and the next topic is essentially to use or to learn to use the nested data frames. Nested data frames are nice things because they allow us to do more complicated way of treating the data. So, let's look at a few examples first of all. So there is this nest function, right? Now, what we do is we take our Gapminder dataset, we group it by year, and then we push it into Nest. And we create a new dataset, which is called by year. Now, if we print it, we get a very interesting structure here. So you can see that the data sets or tables in R, they can be nested. So what we have is a year, right? And for each year, there is a table which contains all information for that particular year. So this is sort of a very, very convenient thing here, right? I mean, you can see that, that you can then include, for example, for this particular year in that particular table, you can include a model, right, for that particular year or replicable to that particular year. And you can play with it, so it just adds a lot of flexibility for you to how to work with this data. Okay, so again, yes, the column data is very, very different from what we've seen so far. But if we print one of them, so we take our by year data set of data sets, right, and print data from 1 to 2, we will get as the output one data set. You can see it on the screen, right? And this corresponds to the by year data 1, which would correspond to 1952, okay? And then in the next frame, we will see the same data frame again picked for a that's interesting that that there is a change in the number of digits here, right? So we will have the same frame, however, for the next year, which is 1957. Right? So you can already, I mean, in principle, imagine that this is convenient thing, right? Because we can easily extract the whole data set without filtering. We can extract it and just work with it for as long as we want. Okay. Right. Now, to reverse the operation, we can do just unnest. Again, we took by year the data, the data set which we have created. So this is the data set which we have created here by year. We created it using nesting, right? And then we just pushed it to unnest. And well, we didn't declare a new name here, a new data set, because it's unnecessary, because we literally haven't done anything. But again, if we put it to unnest, it just unrolls all those nested sub data sets, if you want, right, into a big data set, which was our original data set. And this is how it looks like, right? So we can compare this one with the one which was there in the very beginning, was this one, right? And you can see that this is a table of the same size, 1704 multiplied by 6 columns, and I think even the structure is preserved in this case. Yes. So, no, actually, no, it's not. It's not preserved. You can see that that now it sorts by year. So that's one of my recommendations to you. First of all, there is well, I mean, you should never use direct indexing, right? Because this is the thing which can happen. You think that, after an operation, the order hasn't changed, or the order in the data hasn't changed. All those are individual records, isn't it? So you can literally shuffle them however you want. And in some functions, R is just a little bit too much flexible with it, a little bit too free with reshuffling the data. You may have noticed this behavior if you try to play with data tidying functions. So there is that pivot longer and pivot wider, and there are their old, I already forgot what their names are, their old counterparts, which have been replaced by pivot longer and pivot wider. And if you try to play with that, you were able to see that that there is a difference in the data sets, which comes from the fact that R does not care about the order of the data when we work with the independent data records. The actual representation in the memory, which we can see here, for example, it may be ordered in a completely different way from what we have seen before. Here, it's sort of logical in principle, So because it was again, it was nested by the year, right? So we forced it again. So we forced it to be nested by the year, okay? And when we unnested it, it started unnesting again, tibble by tibble, okay? But it will not be necessarily always the same order as we have put it in. This is why direct indexing is absolute no-no. So you should not use direct indexing when you work with rtables. Okay, you need to always use filtering by the actual values, or you need to pick up the actual values from the variable names. But direct indexing is no at all, right? So because there is like 99% chance that your program will break, will stop working, and will crash. It will be caused by the small change in the data set or small change in the library after an upgrade. So you should never ever use direct indexing. Okay, right. So let's go on. Now, what is good about it, about nested data sets, is that we can use them to fit a number of models. For example, in this case, we create literally a model for each year, okay? So, and now you will see a very interesting thing, how the data is represented, how all this is represented then. So what we create is a, well, function which creates a model, right? A model is an object, so it creates, after calling, it creates an object with the fitted model to a particular data we feed it in. Again, so the model works on the data frame which we put in. In the data frame, we expect the variables of life expectancy, and then we put GDP per capita and continent, and we put all the interaction terms in it. So we will have GDP per capita as the individual variable, we'll have continent as the individual variable, and we will have the interaction term of GDP per capita by continent. Okay, so we expect to have all the flexibility we have just introduced. Now, we declared this function. Now, what we can do is we can go through the data set year by year, right, and add the column models, right? So this is what we do here. We take our by year data set, which we have created. So each element in this data set, in this table, is a data set itself, right? Then what we do is we create a new column model, which is created by mapping the data into the year model, right? So we take the data here. The data is the variable which contains tables for each particular year. It pushes it into the year model, which creates the linear model for that particular year, right? And then a new column is created from that output. So you can see that you don't need the loops. You don't need the direct indexing. You literally use a one single line of code there, because R essentially, R allows you to do that, because R is specifically designed, to have that in mind, to remove the need for loops completely. Okay, and there is this function map, which is very nice, which literally takes an element from data, puts it in, and creates the, so it acts like a loop, and there is indeed a loop inside there. It's just you don't need to use it. You don't need explicitly to use any loop. And it's like one line, one small line of things. Right. Now, when we print what we have created, which is by year, we'll see a very interesting thing here, right? So what we see is, again, is the old variable year, then there will be the table of the original data, and then there will be this object of the model, which is associated with every data record in our new data set of data sets. So you can already see how convenient it is, right? you have created like how many 12 yes 12 rows corresponding to different years, right? You didn't do any loop, you didn't do any manual input, you just ran through all those years, created the data and created and generated the model on that particular data corresponding for that particular year, which is very nice. Now, we can also generate the multiple plots. So what we have here is a function which is which aims to plot the fit, right? What we do is we put the data frame and we put the variable year just to have the title, to have a separate title for each of the plots, okay? Then we take the data frame, put it into ggplot, and plot the GDP per capita versus life expectancy. We put the continent as a color. Now, note how we use it here, right? Continent is a factor. Continent itself is represented somewhere in the memory of R by a number, by an index, right? So this is how we converted the categorical nominal variable into a nice representation which R uses. So here it is a number, right? But this number is not a metric variable. This number is still a label, right? But we can use this number to assign a color for to every plot, right? Okay, and then we add on top of that the geom smooth with the linear model on top, right? And we do not plot the standard error on top, although we can put true here and we'll see what happens. And then we also put the title for every plot. Now, note that this is just one function, right? So what we will be able to do is the same trick as we have already done, right? We will be able to take this map, however, with two parameters now, right? So there will be X and Y because we need two parameters here. We'll take data, we'll take year, and everything will be pushed into the function plot fit, okay? And again, so that will create the plots variable, okay? In the by year data set. So you can see that plots are also objects which can be put in the in the data frame or in the table, okay? And then we use we use there is one more library which is GridExtra. You probably, I mean, you may need it often, I would say, but just to know that that it works like this. Now, what is happening here is even more interesting, right? So we take our data set, we filter the year by belonging. So there is this percent in percent belonging to this vector, which is 1952, 62, 72, okay? And then we put it into the grid arrange. This is coming from this GridExtra, where each of the plots will be from $dollar plots. Note that we have created a variable in by year data set, and that variable, which is named plots, it actually contains plots as objects, right? So this is again very interesting thing here, which we are looking at, okay? And we put it in one column, so we can write it, right? So we can run it. And this is the plot which we get. We literally take every sub data set for each particular year and fit there that linear model that we have fitted, and then we plot it again using the this literally, right? Because because each of the plots is an object in our big big data frame. Okay. So it's a very convenient thing, literally, well, it's powerful because you can do a lot of things with it. Okay, so now the next question is about that cross-validation. We looked at the cross-validation in this lecture. So you remember what cross-validation is, a k-fold cross-validation, except that in this case it's not k-fold, it's v-fold cross-validation. I don't know for why they used v instead of k, but okay, right? So what happens there is, again, is we divide the data set into a number of parts, into 10 parts, right? One of those parts is used as a validation data set. The other parts are used as the training data set. So what we do here is we take our Gapminder, right? And we do it by year. Okay, so we stratify the data set by year and we perform the 10-fold cross-validation. Okay. Also, this is done randomly, and if we want our results to be completely repeatable, we can set the seed, as I have told you in the first practical. Okay, so we can run it, right? And what we have here is the new data set, right? Which contains those splits, right? And which contains also the ID, which is called fold 01, fold 02, down to fold 10. Okay, so we specify here 10 folds, and we've got the data rearranged, randomly reshuffled into 10 folds by year. Okay, so let's just look at one of them. Okay, and so each of them will have the will have two parts, right? So each of them will have the training part and the testing part. They are named differently here. They are named by analysis part and assessment part. So analysis part is the training part, right? And the assessment part is the validation part. Okay. So each of those folds has two parts. One of them is training, the other is testing. Training is called analysis, testing is called assessment. Let's look at how they are split. Now, you can, of course, in principle tell here that you want to split it in a different way, but okay, yeah. So yeah. So what we have is the number of records in each of those, and we can see that the analysis or training data set is a big one, and it has 1,532 data records, right? And the assessment part or the testing or the validation part has 172 records. Now, you can see that originally we had how many data records? 1,704 data records, right? And this is what we've got here. So we've got 10% for the testing part and 90% for the training part. Note that it nicely rounded it so it uses all possible data in the data set, right? So when you sum them up, right? When you sum them up, everything aligns. It's interesting that no, everything is fine. No, everything is fine. So it's 172 and 1,532. So you can use this dollar splits one to see how the training and testing parts of the data set are split and how they are balanced. And you can see that, again, analysis part has a lot of data records, right, 1,500, right? Assessment part has 172, and in total it gives 1704 data records. So let's just go again and check that that we have 1704 data records in the data set. Okay, so far so good, right? Now you can see that we are sort of going into this machine learning implementations or standard way of performing machine learning when we are not able to to design the things like AUC. Sorry, not AUC, but AIC, AKK information criterion, right? And we can use it in any case. We can use it for the linear model, of course, right? So there is nothing, well, absolutely wrong to use it for the linear model, except that there are those reasons which I have outlined you in the lecture. The estimates will be noisy and it will take time. For such a small model, time is not a problem, right? And noisy estimates are also not a problem in principle, because we are not going to, to launch a satellite based on that. Right? But in the case when, when there are critical applications where timing and precision are important, where noise is not allowed, you would need to go back to AIC or some sort of a model-dependent analytically derived criterion for the precision of your for your model performance, not necessarily precision, but for the model performance. Okay, right. So now we can do, the standard process of machine learning exercise. We will take the training data set, which is in this case called analysis data set, right? Perform the training of the model with the analysis data set, and then we will be able to assess the quality of the fit with the testing or validation data set here, okay? So this is what we do, right? We create our fit, first of all, which uses only the analysis part of the data set, right? So we create the function fit_gem, which depends on this SPLT variable, and we put that into GEM with all the parameters inherited from the input here, right? And we put the data, which is equal to analysis of the data set we put in, okay? So also we do the prediction part, right? This is something which is supposed to work on the data which hasn't been seen. So we create a model, we find the coefficients of the best fit, and then we use this coefficients of the best fit to see how it works on the data which hasn't been seen by the model. Okay, and again we use the we create a new function which is predict_gem, right? What we put here is the data set, then we put the model, right? And again, we have this new data, which is just the assessment part of the data set we put in. Now, note that we do not generate it, right? We use broom_augment function, which will just add the which will use the model and the input to produce the prediction. Okay. Now, what we do is the next step is to fit the model. So we take our RS. So this RS object is the output of the Vfold cross-validation dataset generator, right? So we take this. Now we create a new column which is model. So for each of the entries there, for each of the splits in here, right, we will create a separate model, right? So we create that separate model again using this map function. By the way, why am I? No, okay, all right. So using this map function, which literally will iteratively go through the input list, right? Then it will put it into fit_gem, which is our function for model fitting, right? And we put the parameters in here, which is nice because I mean we literally can can use those triple dots to forward everything into the, into the GAN, okay? And we here establish the GAM where the life expectancy is correlated with the GDP per capita plus smooth on year. Okay, so we add something more, some more complicated behavior on the year. Okay. Now I forgot if I ran this. Okay, so now I can run this. So I have created the model in or the models for each of the folds in my cross-validation dataset. And then we can, well, using literally the same thing, right? The same application of the function map. In this case, it's the application of map2 because we have two arguments. We can make the prediction. Now, note that we have now 10 models, right? And we have 10 splits of the testing data. But we need to apply each model to each of the splits. Okay, so we use here map2, which will go through each of the splits, through each of the models, and will execute this predict GAM, where we take the split, the model, and we augment the data into this predict GAM. Okay, and we run it. So we have the new again. New data set which has the table of predictions here, right? So again, that table of predictions will contain application of this particular model to particular to each of the prediction, to each of the folds. Okay, now we can then calculate the error for each of the folds, right? And again, what we do here is use this map double. So we take the prediction, we put the function in which calculates the RMSE of the estimate, right? And the model, and we use the life expectancy. Not sure what this dot fit. Yeah. So this is, this is the actual data, and this is the fitted value. You can see how that fitted value is used. And we can run it again, and it will produce the bar of the errors for each of the folds, applying each of the models, right? Again, so here the error is the RMSE root mean squared error. Okay. Yeah. So, and that's that's basically it for today. So again, to reiterate, what we have looked at today is quite a number of interesting things which may be useful in your future life. Okay. So first of all, we looked at what the interaction terms can do. So they can make your life simpler. Despite this definitely shows a nonlinear sort of dependency, right? When we divide the data set by different continent and start fitting different linear models for each of the continents, we get a lot of improvement. Right, so here we can see that that all those dependencies on of life expectancy on GDP per capita are different, right? And you literally take here into account the complexity of the model, of the data, while keeping the model itself very simple and linear, which will be described just by two coefficients, right? So, and we took into account just the interaction between the continent and the life expectancy, and the GDP. Okay, and then we looked at a very useful thing that we can create nested data sets. Again, each data record contains a data set in it, right? So this is, and again, and we can put into that table again a number of data sets as well if we want to, right? So they will be there will be multiple nests and so on. Now, this is useful because we can use the functions like map, right, for those tables, and we can literally take each of the tables where, where the data structure is embedded and use that whole data structure to create a model or to plot the things. And we have seen that, that plotting the things is also quite interesting and fun because plot itself is considered as an object. And also, finally, we learned how to use that, or how the nested data sets are used when we divide the data set which we are given to perform cross-validation. So we divide it into training and testing parts, and we do it k-fold, or in the case of R, it's v-fold. Yeah, and we have seen how this data set of data sets is created, and then we generated the model for each of the folds we created from the original data set. Okay. We also looked at how the things are balanced in there. So if we don't specify, so if we specify V, it will divide it not 2, but 1 to 9, right? And then essentially, then we fitted the linear, not the linear, but GAM to each of those folds, right? And we were able to check the performance of the model by plotting the error. Now, note that the errors are quite big, right? So this is the error in the life expectancy estimated. So you may want to to consider other factors here as well. Now, this practical is very much based on the Gapminder example in section 25.2 of R for data science, right? And you can literally go into that book and check what is written there, okay? So you will be able to, if you want, to go through the written material, let's say, you can just go and check how it looks like. Okay, so that's it for today. It was fairly short practical, but there is a lot of interesting things. Now, what you want to do is, again, since you will be looking for jobs once you complete your masters, right? And there are those masters level jobs, which are actually quite good in Australia, because I know that the guys who have finished this unit in particular, and in general our master's program, immediately get hired by Australian Bureau of Statistics, and they are quite happy about it because they get like 90K starting salary, which also grows fairly quickly, as I understand. Yeah. So you do want, to know how to use the standard machine learning route, because you may be explicitly told that, that, okay, well, you do want to use here some sort of a deep learning mechanism or something like that, right? And then you will have no way around doing the k-fold cross-validation, because there will be no analytical treatment. However, I want to remind you again that those linear models and GLMs and GAMs are very useful because they are tractable. Analytically, they are explainable, and you literally can, when you think about logistic regression, this is the question whether we decide to activate something or we decide not to activate something, right? In the case of deep learning, it will be hard to explain, and also there will be problems, or there may be problems. In the case of GLM, you can easily explain why the decision was such. That's it. And then you will have no problems. Yeah. So that's essentially that's all for today. Thank you very much. Do you have any questions? Okay. Okay. Okay, good. Again, just to remind you, if you have any questions, drop me an email and I will answer it. Okay? So this all is, of course, applicable to the assignments, to the quizzes. The only thing which I'm not able to answer you is about the exam scheduling, right? So you I don't remember if I've told you, but again, the exams are sorted at the level above the School of IT. The exams are sorted centrally at the university level. So there are, the questions about extensions for the exam, don't even try, because I mean, I cannot do it physically. Technically, I just cannot do it at all, because there is no way there is no mechanism I can give you an extension for the exam. Yeah. Or, whatever, or not extension, but rescheduling. All that has to go through the university. And so essentially, you don't want to reschedule the exam, because if you go into exam rescheduling, it can be rescheduled for plus 1 year or something like that. This unit runs once a year. And if you reschedule it, it may be for next year, and you do want to finish your master's successfully on time and graduate and go and get those jobs in Bureau of Statistics. Yeah, okay, all right. So thank you very much. I can stop the recording now.